Okay, so let me start with a little clarification of terminology. Uh, you're gonna hear this word expression a lot, namely quantum gates. And quantum gates are nothing but the unitary operations on states. And of course, this word gate comes from the classical computation where you apply various operations to modify the states of your bits, not qubits. And these modifications take place through these physical devices that, for historical reasons, were called the gates. And so you combine that word from the basically the classical semiconductor science with the quantum to arrive at quantum gates. But mathematically, this is the same as performing some sort of unitary operation on these state. So I give you some initial state, then I perform some unitary transformation on it, followed by a second unitary transformation, followed by a third, and so on, until your state reaches the kind of state that you find most useful for a specific purpose of quantum computation. But each one of these unitary matrices is really 2n by 2n dimensional unitary matrix, right? Because this is a state of the n qubits, and each state has two possible states. So if you put together two possibilities for n qubits, then the total number of possibilities is 2 to the n. That's the dimension of the Hilbert space for the n qubit system. Which means that any unitary operation acting on this state is necessarily 2n by 2n dimensional. But that's a really big unitary matrix. And not only is such a big unitary matrix difficult to handle mathematically, but it's also very difficult to handle physically. Okay, because performing such a unitary transformation means that you kind of have to access all of these n qubits simultaneously and perform some intricate operations on all of them at the same time with basically infinite precision. And that's obviously going to be a very challenging task, engineering problem for anyone to accomplish. So, what we would really like to do is to kind of break this each unitary transformation down to something much simpler. That is, I want to break this down to a unitary transformation acting only on the first two qubits, while all the other qubits are sitting idly by, like that. So although this is formally a 2n by 2n dimensional unitary matrix, its actual content will only be 4 by 4 dimensional. And a 4 by 4 dimensional unitary matrix is something one can handle not only mathematically, but also physically. Let's say you put some electrical contact here, and then you do something to the electric contact so that the content of both of these qubits are modified in a certain way. And that's something that you can hope to accomplish with more or less perfection uh, in a real life. Okay, but then the question is, but then the question arises: are all interesting operations when we say operations, we of course mean unitary operations. Are all the interesting unitary operations made up of 2-qubit operations? Okay, so the question is the following. I want to accomplish some complex 2n by 2n dimensional unitary operation on the initial state. The question is whether it will be possible to find a decomposition of this enormous unitary matrix into many pieces of much simpler unitary matrices, where each unitary matrix is basically only 4-dimensional, while all the other components in the tensor product are just the identities. Well, surprisingly, the proof that this is the case is actually quite simple to accomplish, and I'm going to show that how that works in the case of a 3-dimensional 3 by 3 unitary matrix. And once we know how to do that, then generalization to an arbitrary d by d unitary matrix is going to show up in a very straightforward way. Okay, so here's the proof. So I give you this unitary matrix, and it's 3-dimensional unitary matrix with components H, K. And of course, not all of these components are independent because they has to satisfy this unitarity condition. But actually, it doesn't. You don't have to bother with that too much, as it turns out. Okay, so now I'm gonna start with this arbitrary 3-dimensional unitary matrix, and then I'm going to introduce this following basically 2-dimensional unitary matrix. Okay. Okay. So this is in the block diagonal form. Okay, which makes this effectively a 2-dimensional matrix, unitary matrix. And now, when you multiply this matrix to the left side of the of this 3-dimensional unitary matrix, something very interesting happens. Of course, this is a pretty complex multiplication, so we're going to see a lot of terms, a lot of very complicated looking terms. But the key point here is that this second element in the first row, first column, becomes 0. Okay, so the whole purpose of introducing a unitary matrix that has this form is so that when this multiplication is done, this second element becomes 0. Okay. Now the next step is to introduce a another essentially 2-dimensional unitary matrix, so that when multiplied on the left, I will have also the third element equal to 0. Now, it should be pretty clear that if I can accomplish the task of making the second element disappear by multiplication with some two-dimensional matrix, then it should be no harder to find a similar unitary matrix when multiplied will result in 0 for the final element in the first column. Okay, so I'm not going to write down the explicit expressions of the U2. It has already been written down in my lecture note. You can look up to that. Look that up. Now, so this is a unitary matrix by assumption, and this is also unitary matrix. You can check, and this is also unitary matrix. And when you make a product of unitary matrices, the result is still a unitary matrix. Okay, but the thing about the unitary matrix is that every column vector is orthogonal to every other column, and also every column vector has to be normalized to a unity. And the same statement applies to every row vector. So each row represents some sort of a vector which is normalized to unity, and they're orthogonal to the rest of the row vectors. Now, what that means, in fact, this you can prove that with the suitable choice of a U2 dagger, this first element in the first row or the first column becomes 1. Okay, but then this first row has to be a unit vector because that's just a general property of a unitary matrix. But in order for this first row to represent a unit vector, then these two other elements must be 0. Because the first element is already 1, so to satisfy the unit normalization condition, then these other elements must vanish. Okay, so what happens is that we were able to decompose this into a nice block diagonal form. So let me recap. So given arbitrary unitary matrix U, I can just go ahead and write down these basically two-dimensional unitary matrices, U3 and U2, so that their multiplication results in this direct sum of a unitary matrix into this form. However, since now this submatrix, 2x2 submatrix, is also going to be unitary matrix, and finding the inverse of a unitary matrix is really just trivial, because by definition of a unitary matrix, okay, so all you have to do is take the Hermitian conjugate of that matrix, and that automatically becomes the inverse matrix. So I can call that inverse matrix U1 dagger. And by multiplying such a U1 dagger to the left, I will finally accomplish the full diagonalization of these original U matrix into unit matrix. Okay? And lo and behold, each one of these unitary matrices U1, U2, U3 is basically a two-dimensional unitary matrix. Okay? So now I'm going to multiply the inverses of these things to the left to show that this is U becomes the product of these three unitary matrices. Okay? So I started out with some arbitrary 3 by 3 unitary matrix. And what I was able to show is that it basically breaks down as the product of three different 2 by 2 unitary matrices. Now, obviously, this argument generalizes, right? So if I have a unitary matrix, which is some 4 by 4 thing, then going through the same argument, similar argument as before, I can find a set of matrices and now there's going to be 4 such matrices. Upon multiplication to the left of the original 4 by 4 matrix in succession will turn the original 4 by 4 matrix into a unit matrix. And therefore, U becomes a U4, U3, U2, U1. Now, the point is that each one of these is effectively, so this is some arbitrary 4 by 4, but each one of these is effectively a 3 by 3 matrix. Okay. And then you can apply the previous logic to each one of these and reduce this 3 by 3 matrix into a product of 2 by 2 matrices. Okay, so this way actually we have shown that okay, let me write this in a slightly more formal way. I give you some d by d dimensional matrix, and then I'm going to multiply on the left hand side by a string of these matrices. With the result that it basically becomes a direct sum of a one-dimensional matrix and d minus one-dimensional unitary matrix. Okay, and then you can apply the same logic recursively to the unitary matrix that has effectively a one lower dimension. Okay, so to decompose a d-dimensional unitary matrix to a unitary matrix of one less dimension, the most that you require is d minus 1 number of unitary matrices. And at the next stage, you will require d minus 2 number of unitary matrices, and so on until you finally will require only one matrix. So at the most, there will be only this many matrices in order to completely break down these unitary matrix into much smaller units. Okay. So now this sort of mathematical proof gives us an assurance that as long as you can perform some two qubit operations reliably, then that will be able to perform all the unitary operations reliably. You just have to apply those two qubit operations a sufficient number of times over a sufficient number of the variety of two qubit systems, subsystems. Okay. And that's a great advantage for the quantum engineers who try to go ahead and build a quantum computer because the limit is basically set at the two qubit control, at the level of a two qubit control.